Okay. Yeah, so hello everyone. It's our pleasure to have Zhan here to share his works to us, like on probable advantage of parameterized quantum circuits in function approximations. Yeah, Zhan, the floor is yours.
Yeah, thank you. Thank you for everyone for coming today. And the topic today is provable advantage of PQC in function approximation. It's a joint work with my collaborators in Wuhan University and Hong Kong University of Technology. And I'll first show you the outline of my talk today. We will first introduce the basic ideas of quantum machine learning and the concept of parameterized quantum circuit, PQC, and also a special type of PQC called data uploading PQC, and also the universal approximation theorem of PQC. And also we will introduce our main result of this paper, which is a quantitative function approximation result of using Bernstein polynomials and local Taylor expansions. And finally, we will analyze the quantum advantage of our proposed PQC over deep neural networks. So first, the concept of quantum machine learning, which is actually emerging area of combining the techniques of quantum computing and machine learning to, achieve some advantages over classical machine learning. So we could, based on the pictures that show on this slide, we could define different types of quantum machine learning. Depends on the type of algorithms and type of data. So today we will focus on one special type of quantum machine learning, which is where the data is in classical. Is the classical data, and the model is the quantum model. So now that the goal is to achieve some advantage over the classical machine learning, we could think of some possible quantum advantages. So here we introduce some essential aspect of quantum machine learning, which we could use to measure the performance of the machine learning models. The first one is the optimization. So optimization is to characterize the ability to efficiently converge to a global minimum. So which means when we have a model, we have some training set, and we want to train our model on the training set to minimize the loss function. So the optimization is just the ability, could be think of the trainability of the model. So if we could easily converge to a global minimum, we say, the trainability of the model is good. And the second one is generalization. So based on what I said before, our training is based on the training set, which means we would have some example input and outputs of the data. But finally, we will use that model on some unseen data, which means we need to guarantee that our model will have good generalization ability, which is ability to adapt the model to the unseen data. And the last one is the expressivity, which is the ability to approximate or represent the functions, which is the main ability that we will focus today. So based on the picture that I show here, we actually could define the arrows of machine learning model into three parts, which is the training arrow corresponding to the optimization, and also the estimation arrow corresponding to the generalization, and finally the approximation arrow corresponding to the expressivity. So we're moving to well-known quantum machine model called parameterized quantum circuit, PQC in short. So for the left-hand side is the classical feed-forward neural network with FNN, which you probably are already familiar with. So we can see in this structure, we have input data. We could input data to the input layer and which is connected to different neurons. And using this layer-based model, we could adjust the weight between like each between the connection of each neurons. And finally, we will have some outputs. So the training of the FNN is actually to adjust the weight in that model. And similarly, in quantum computer, we could define some similar parameterized model called PQC, which is based on, based on the similar idea of the FNN. The only difference here is that because we need to process the classical data, so we need to first have to encode the classical data into the quantum circuit. As you can see, at the first of the PQC, we'll have a data encoding circuit, which is used to encode the classical data. And then followed by a trainable circuit, which is the parameter corresponding to the adjustable weights in the FNN. And the outcome is actually the measurement result of our quantum circuit. And the training process is just to adjust parameters in the trainable circuit. Yeah, that's it. So do you have any questions on the definition of the PQC that I present here? Yeah, I think it's sort of clear, yeah. So other than the PQC that the commonly used PQC that I defined before, Pelesenius et al., they define or say propose a new type of PQC called data uploading PQC, because they observe that the classical artificial neural networks, the data is actually uploaded to different neurons for multiple times, which is quite different from the previous PQC, the classical, the previous PQC that I defined before. So they proposed a new type of PQC, as shown in the right-hand side. In this model, we can see that the classical data is actually also uploaded to the quantum circuit for multiple times. So basically, this type of PQC consists of interleaved data encoding circuit S and trainable circuit V. So based on my understanding, I think it is a more similar model to the classical neural networks, because here we also have this sort of ability to upload the inputs to the quantum circuit for multiple times, which will possibly enhance the performance of the PQC. So let's also recall some foundations of statistical learning. So in the supervised learning, actually, we just propose a training set, which consists of examples of input and output. And based on this sort of training set, we build a function that maps new data on the expected output values. For example, for the classification tasks, such as the image recognition, we just train our model based on the examples of images and labels, and then we get some new inputs. For example, images of cat and dog, and the model will tell us whether the image is a cat or dog. And also for the regression task, which is also similar. For example, in the house price prediction, we also train our model based on the features of the house, and their corresponding price, and given new features of the house, we just make a prediction of the house. And actually, in this kind of learning process, the mathematical foundation lying behind them is actually to approximate or say a learn function from a finite set of samples, which is a training set. So the expressivity is defined as the function that a machine learning model can express or approximate, just as we showed before. And the important concept in the expressivity of machine learning is the universal approximation theorem. So I think it somehow explains the reason why that the neural network work. So at first, I think it provides a theoretical guarantee, which is that FN are actually universal approximators. Based on the theoretical result, it has been shown that FN with one hidden layer and arbitrary width can approximate any continuous functions, which is the theoretical guarantee of why the FN work. So now that the classical neural network will have this sort of guarantee, how about in the quantum setting for the PQC? Also, in the quantum setting, we also have some results showing that data uploading PQC are also universal approximators. For example, in the univariate case, it has been shown that we can construct explicitly construct single qubit PQCs that can approximate a univariate continuous functions. And for multivariate case, it has been also shown that there exists some multiple qubit PQCs that can approximate the multivariate functions. But the proof is not constructive because it assumes effective Hamiltonian encoding for the data and also assumes arbitrary observables and arbitrary trainable unitaries. And the idea is actually to use the PQCs to represent the Fourier series of the target function based on the previous result.
So you're over here for what you mean by constructing proof is that we know the exact Hamiltonians of observables and the unitaries to construct like whatever function they want.
Yeah, for the single qubit case, which means I mean the explicit construction just means that we know what kind of gate that we use and how many gates that we need in order to, achieve some, certain degrees of Fourier series.
Right, just like some quantitative way of like characterizing the.
Yeah, and we will show that result after.
Okay.
Yeah, but for the multivariate case, the most important thing is that it's not constructive.
Okay.
There are many assumptions.
Mm-hmm.
So the next we will talk about the problems that we want to study. The first is the problem of the universal approximation theorem. The main problem of that theorem is that it is based on the existing proof, but it's not quantitative. So all the universal approximation theorem, including the classical and the quantum one, just tells us for some types of functions, there exist some quantum circuit or some models that can achieve arbitrary good approximation results. But it's not quantitative. It just tells you that there always exists one, but you don't know how large it is or how it looks like, something like that. So, which means we cannot determine the necessary size of the model to achieve some arbitrary, some desired accuracy, approximation errors. So it implies that if we want to study the quantum advantage over the classical model, we cannot just use a universal approximation theorem because it cannot tell us any quantitative result. And recently in classical learning theory, some quantitative approximation error bounds have been established in terms of width, depth, and the number of parameters in the model. For example, the table that we show here is a nearly optimal bound for Relu Fn approximating smooth functions. So given the certain width steps and the number of parameters, we'll have like this sort of certain order of approximation errors for approximating the smooth functions.
So what are those like variable represent? N, S, and D. So
Oh, sorry. Yeah, D is the number of variables
okay.
that we want to approximate. I mean,
S
it's a multivariate function, right?
Okay.
It's not a univariate.
Uh-huh.
And S is characterize the smoothness of the function.
Okay.
So just basically on the S and D.
Uh-huh.
And yeah.
And then N,
Mhm.
N will be the number of layers or
So N is just I mean, just affect the width and depth of the, I mean, you can understand N and M characterize the width and depth of the model.
Mm-hmm.
And you can choose N and M.
Okay.
Yeah.
Right.
But so based on this quantitative approximation error, we do have this in the classical learning theory, but for the quantum setting, we don't have any relative result. So it makes it hard to compare whether the quantum machine learning is better than the classical machine learning or it is worse than the classical model. So that is a problem that we want to solve in our work. So to solve this problem, we use some basic tools is to use PQC to implement polynomials, which is like in the univariate case, we just show that we have some constructive proof such that we can use a single PQC to approximate a univariate function. So if we use the data refolding model that we I mean introduced before, we just let the data encoding gates to be the I mean they're all rotational gates to be Rx gate. And we just input our, we just do a like arc cosine encoding for the classical data and input our classical data to the poly-X rotation gate. And for the trainable gate, it is simply RZ rotation gate. And based on this kind of interleaving data reuploading model, there are theoretical results showing that we can use this model to implement a polynomial if and only if the polynomial is L degree real polynomial. I mean, the here, because we can see that in this sort of model, the data is I mean uploaded for L times. Let's assume that. Then the polynomial is real polynomial with degree L. And also it has some parity constraint, which is L mod 2. Here we say a polynomial has parity 0 if it is even polynomial. If it is a parity 1, then it is odd polynomial. And also have some extra constraint saying that the polynomial should be bounded by 1 for all x from -21. So that is the result of using a single qubit PQC to implement a univariate polynomial. But the problem is how to extend to multivariate case, because we know that in machine learning, we always care about high dimensional data. So univariate case is not that interesting. So we use we actually just extend this previous result to generalize to the multivariate case. If we consider a d-variable polynomial with degree s, which is defined in the first equation, we could see that the d-variable polynomial is actually in a combination of monomials. I mean, multivariate monomials together. So the first step is actually to implement each multivariate monomials, say C alpha x cube. C alpha XGR. So implement this is actually pretty easy based on our previous based on the previous result of the univariate case, because we just simply tensor product the previous single qubit gates, and we do the measurement, then we get the multiplication of univariate monomials to get a multivariate monomials. So this one is a pretty trivial one. And based on the degree of the monomial, we also have the known width and depth and number parameters in this sort of simple circuit, because here we don't have any, say, entanglement or something. It's just a pure tensor product. So having this, we could just simply aggregate monomials together to implement the polynomials, right? Classically. But actually, in the quantum computer, the sum of unitary may not be a unitary, so we cannot just add unitaries together on a quantum computer. So that's the problem. So to solve this, we need to use a linear combination of unitaries technique to achieve the linear combination of the sum of unitaries. So that is the circuit of LCU. So basically, it's just multiple control of each unitaries, and so if the number of terms in the summation is t, then we just do from one control the first one, and to the t control the t's one. So so that's basically the quantum circuit of LCU to implement the linear combination of unitaries. And having this circuit, we could do the inner product to obtain the multivariate polynomial. To do that, we can just simply use Hammer test. So having this, so based on, so having this quantum circuit, we just know that how we can use a PQC to implement multivariate polynomials, and it is actually a constructive proof on how we can do that. So, and also one thing I want to mention is that this construction is also space efficient, because the first register is actually the number of qubits in the first register is actually log t, right? Because t is the number of items in the summation, and typically in the polynomial, if we want to say to have some high order polynomials, actually the number of terms in the polynomial is exponentially small, many. So yeah, based on our previous construction of the PQC that implements multivariate polynomial, we could use that to implement the Bernstein polynomial of any continuous functions, which is defined in this equation. So, and also given any Bernstein polynomial of some unknown some continuous function, we also know the width steps and number of parameters based on our previous construction. And also based on the Weierstrass theorem, the Bernstein polynomial will uniformly converge to the continuous function itself as n goes to infinity. So here we actually prove that the PQC that we construct before, we can use that to implement Bernstein polynomial of continuous functions, so that it is a universal approximator for continuous functions. And also, if we say add more constraint of that function. Say it satisfies some Lipschitz condition. We also know some quantitative error bound for using a Bernstein polynomial to approximate that continuous function, as shown in this sort of theorem. But if we look at this theorem, we will find that if we want to achieve a relatively small approximation error, we may need to construct a super large PQC, because as you can see in the error bound, which is not what we want, because if we use this quantitative error bound to compare to the classical model, we will find there's no quantitative advantage, because here we also have some exponent. We also have some like curse of dimension to achieve some arbitrary small approximation error. And to further improve the result that we presented before, we're thinking of using local polynomials to replace the global polynomials that we introduced before, just like the Bernstein polynomial. So if we compare using global polynomials and local polynomials to approximation the same functions of using the same degree, we'll find that the local polynomials tend to work better than global polynomials. Because in the local polynomial part, we will divide the entire region into some small pieces, and we just do the approximation on the small pieces. And in this case, which it means that the polynomial the entire polynomial that we are using is not continuous, because we need to first divide, to localize the entire region. So that is the idea. And also for the local polynomial case, I think the most commonly used one is the local Taylor polynomial. It's a local Taylor series to approximate a function. So local Taylor series tend to approximate the function well on a relatively small region. So that is the idea. Then we could use the Taylor expansion of some smooth function to do the approximation. So here's the definition of some smooth function, which is called a beta Holder smooth function. The mathematical definition seems complicated, but I can maybe break down this class of functions when we consider different beta. So when beta is between 0 and 1, it is actually a class of Holder continuous functions. And when beta is equal to 1, then this type of function is actually the Lipschitz constant, a continuous function with constant, with some constant. And when beta is greater than 1, then it's just some smooth functions whose s partial derivatives exist and are bounded. So that's a definition of the target function that we want to approximate. And based on this type of function, if we do a Taylor expansion of this function, we'll find the Taylor remainder is bounded by, as shown in the second equation. And based on this approximation error bound, we'll find that the Taylor local Taylor expansion will have some good approximation performance when x is close to x0, where x0 is the fixed point that you choose. So that's why it's called a local Taylor expansion, because it only works when the region is relatively small. So that is the idea. Then we are trying to, then we have this local Taylor expansion as a tool. Then we are considering how we can use the PQC that we construct before to implement this sort of local Taylor expansion. So we will divide into 4 steps. The first step is the localization, as I mentioned before. So the idea of localization is that given any x, we need to decide the fixed point. We need to choose that fixed point so that x is close enough to that fixed point that I choose. And the second step is to implement the Taylor coefficient, which is we need to implement the part before the x minus x0 to the alpha, which is just some say parameters or some quantities that depends on the fixed point. And the next step is to implement the single Taylor term, which is to implement the x minus x0 to the alpha, which is pretty similar as we showed before to implement the monomials. Because we can just simply replace x with x minus x0 if we know the x0, right? And then finally we just combine the Taylor coefficients and the single Taylor term together, and then add them together by LCU to implement this entire Taylor series. Okay, so yeah, then we follow this like 4 steps to show our construction. The first step is localization. As I said, the task of localization is actually to find the fixed point of some given input so that the fixed point is close enough to x. The idea then is because our domain is 0, 1 to the d, then given this, so for example, in the 1-dimension case, which is a univariate case, we just divide the domain 0 to 1 to k part uniformly. Then if x is in one of the k parts, we just choose the fixed, the leftmost point of that interval as a fixed point. Right. So as you can see in the 1-dimension part, we just choose k to be 5, and we just divide this region to uniformly 5 part. And if x, for example, is in 0 to like 0.2, then we choose the fixed point to be 0, and so on. So that's it. And as I said, if we do the localization, the local polynomial approximation, then our polynomial cannot be continuous. So we just need to also define some traveling region for the discontinuity, as you can see in the green part. And also we can see in the 2D part, which is also relatively simple. We just divide this square into k square small squares. And once the point is inside each square, we just pick the left corner, lower corner of that square to be the fixed point. So that's it. And once we have the concept of localization clear, then we need to design a PQC that we can use to find the fixed point for arbitrary inputs, right? So the idea is also a simple one, because if we just consider the univariate localization function, we'll find that it's just a step function. So if x is between 0 and 1 over k, and we just output 0 as a fixed point, and so on. So it is actually a step function, as we showed here. So the idea is that we use a polynomial of the degree showing the screen to approximate with some arbitrary precision. And once we have the polynomial that approximates the step function, then we can use the PQC that we showed before to implement that polynomial so that we can use that PQC to approximate the localization function. So once we have the univariate location, because we know that for multivariate case, it's just into high dimension hypercube, so we can just simply do a tensor product to extend the univariate case to the multiple variate case. So using this quantum circuit, the PQC, we can actually achieve the localization function for multivariate localization. Okay, so after, maybe any questions for, the localization part?
Now, how should we choose K, by the way?
Yeah, so actually, it is a question that is corresponding, I think corresponding how well you want your model to approximate target function. So basically K is large. When K is large, which means the distance between the point and the fixed point is smaller, which means the approximation error is also smaller.
Ah, okay. Like now it's kind of bring back to the equation that you showed.
Yeah.
It's bounded by the distance between your point and the fixed point.
Yeah.
So that,
In this case, the distance between the point and fixed point is 1 over K, right?
Right. Yeah.
So when you increase in K, then the distance increase or decrease. Then you have better approximation result.
Right. But how does this reflect in the cost of implementing your PQC? Like, is it like more layers or more qubits that you need? I couldn't really see over here.
Yeah, here with steps.
Okay, so it's reflected that.
Yeah.
So if the larger the K and
then you will need more.
Okay.
You will need a deeper PQC to implement that.
Right.
Yeah.
If you're actually doing like localization, suppose your function that you wanted to has like some noise of perturbation, aren't you actually learning the noise as well? Like as in you overfitting?
The noise of what?
Suppose your function is not exactly a noise, so it has some perturbation.
Yeah.
And you don't want to learn the perturbation. So if you like do localization, what is like learn the noise?
I guess for the localization part, it's not depends on the target function that you want to do. It's just to implement this kind of set function. That is here is the target function that you want to implement using PQC. Yeah, so is that okay?
Partially, you can do one. I'll say that.
Okay, yeah. Maybe your question, you can ask it later, maybe. Yeah, just for the localization part. Okay, then we move on to the next step is to implement the Taylor coefficient. So based on our localization, we just divide the entire region to K to the D hypercubes, right? So which means we'll have K to the D different fixed points, which means we need to implement K to the D different Taylor coefficient, because Taylor coefficient is only depends on the fixed point, right? So actually this step is a trivial one because we know that Taylor coefficients have like K to D different Taylor coefficients. Then we want to use a quantum circuit to implement that. Then you need to reduce to a point fitting problem. So we have different like K to D different points, and we want to use a PQC to implement that to fit that point. So here we just use a simple selection unitary to do the data fitting problem, just point fitting problem. So the first one is actually the index of each fixed point. So we will have from 1 to K to D. And the first register is, as I said, you can input the index of the fixed point. And the second register just corresponds to the parameterized quantum circuit that it can implement the corresponding coefficient. So it's just a pure selection problem. So use the first one, the second one will give you the corresponding telecoefficient. So there's nothing much to say about this, but we just need to know that when K and D is given, or say we choose K and D is given, then the width, depth, and the number of parameters is also known for this case, and the circuit is also constructed, right? Then the next part is the single teleterm, which is also a trivial one, because as you remember, we previously implemented PQC to achieve the monomial, the multivariate monomial, x to the alpha. And here, if we use the localization part to know the fixed points, then we can simply replace x with x minus, the fixed point, right? Here, the fixed point is eta over k. I just replace it because, yeah, for the some notation. So then, for the first circuit, is actually the telecoefficient circuit that I showed you before, and the second one is a monomial one. We just replace the x with x minus the fixed point. As we showed in the most previous one. So using this quantum circuit, we are able to implement the single teleterm with telecoefficient and the monomial. Okay, then the next step is also pretty similar to what we have done before, which is using the linear combination of unitaries to aggregate all the single teleterms together to implement the entire local tele expansion of that target function. And also using this similar analysis before, we have certain width steps, and the number of parameters depends on the degrees of the teleseries, and also the k that we choose, and also the dimension of that function. Okay, so that is the overview of the PQC that we introduced before. So if we have some inputs, we just first do localization. So we just input the x to localization PQC, and we do the measurements to obtain the fixed points that correspond to the x. And then when we have the x and the fixed point, then we use the second PQC that we showed before to implement the tele expansion of the function. And then we do a measurement. Then we have the result of using local tele polynomial, series to approximate the function. So yeah, that is the big picture, or say overview of our proposed PQC. And as we said before, if we choose, a certain k, then the distance between the fixed point and the input is bounded by 1 over k. Then we have some bounded error. That depends on k that you choose. Okay, here is also some the calculated width steps and number of parameters of the entire PQC. But you can see here, because it's not just an entire PQC that we measured once. It's actually nested constructed, because we need to use 2 PQCs and use measurement result of first PQC as input of the second PQC. So when we calculate the width and depth and number of parameters, we just simply add them together for simplicity. Okay.
So I have a question over here, because we are doing the measurements and then fit it into the second PQC.
Yes.
Right? How will the sampling errors be propagated? The estimation errors of your observable be propagating throughout?
So actually, for the first one, you mean to find the fixed point when you define k, and you get some measurement result, the error actually can be ignored because you can always do the rounding.
Always do the rounding.
Yes, because you know that a fixed point can always be 1 over k, 2 over k, and 3 over k, and you can always find the closest the measurement result to round them to an integer over k.
Okay.
So maybe we just back to the localization. So for example, here you have some result, measurement result. You have some errors, right? So it is not exact eta over k.
Yeah.
Right?
Yeah.
But it's close, it's very close to eta over k. Up to some epsilon.
Right.
Then you can always, when you get this result, you can always round to this.
Okay.
Right?
So
which means you can always decide the fixed point. It's not depends on the output.
So in some sense, your algorithm is noise robust.
Yeah, it's
everything noise robust. It's not okay.
Yeah. So yeah, that's a very good question. I think the missing part I forget to talk about.
But how about the second part though? Then like over here you have like
which one?
Yeah,
previous one.
So no, as in go to this one.
This one.
So the second measurements, like how do you deal with the second like sampling errors over there after the
for this one, we will typically ignore that because typically in the quantum machine learning theorem, people will tend to use the expectation value to represent the result of the PQC, right?
Yeah.
So actually, when you want to use the measurement result to represent the expectation value, you will have some errors.
Yeah.
So
that one is just like okay, everyone's
everyone's doing so, then we ignore. But if we want to calculate, then it's doable because the result is is obtained using the Halma test. So which means we just need to reround the circuit for multiple times to reduce the sampling error, right? But it will not say increase the depth or the width of the PQC.
Right. Okay.
Right. Okay. So that's the approximation error quantitatively, and corresponding width steps and number of parameters. Then it's time to compare the quantitative approximation error between the quantum machine learning model and the classical machine learning model, which is relevant. For example, we just compare the relevant and with the proposed PQC, and we just list all the width steps and the number of parameters and errors here in the original paper and also in the previous page. And we just consider the case that the smooth index, the target function, the smooth index of the target function is small, and the input dimension is a pretty large one, which is actually common in the real world applications. Because typically the target function would be not that smooth, and also the data feature will typically be a high dimensional feature.
Sorry, could you remind me again, like what is controlled by the smooth index? Like what is the things that are controlled by the smooth index? Like the smoothness of your approximations, or like what? Why should we consider the smooth index?
Yeah, the smooth index actually is, I think, is also related to the approximation error of the Taylor expansion.
Okay, so if the smooth index is large, then you have smaller approximation errors, or the other way around?
I think it is smaller.
Okay.
Yeah, I think it is smaller based on this one because probably larger.
Okay.
Yeah, larger because here you have e to the s.
Right. Okay.
Yeah.
So why do you say you have quantum advantage based on the number of parameters?
Yeah, I will continue to show that. So if we compare these two tables and we just let the approximation error to be the same epsilon, and we just compare the number of parameters of PQC and the number of parameters in FAN, and also compare the size of the PQC, the size of FAN, and we'll find that the size of PQC is sort of exponentially smaller than the FAN.
But that does not imply fundamental advantage. So what is saying is that you can construct a PQC which has an exponentially smaller number of parameters than FNN, and you can approximate the same thing, but that's not the same as quantum advantage.
Yeah, it's not the, I mean, the typical quantum advantage that we show as in say Grover or Shor algorithm. It's not.
No, I don't mean like that. I mean,
Yeah.
like, suppose let's say you have PQC of those parameters.
Yes.
You need to show that first of all the PQC is trainable, right? Because you don't want to be that because a lot of PQCs, when they're deep enough, they form two different structural balance values.
Oh yeah.
And they have a very bad convergence properties, and the number of times you run a spanning function,
Yes.
it's exponentially large, and that defeats quantum advantage. And it's basically previous slide you had your localization question.
Yeah.
Since it's all like single computing unitaries, isn't that exactly developable?
Yeah, that's a good question. I think so. For the classical simulable problem, we're not sure if it is classical simulable, but we guess because we use the LCU to introduce the entanglement.
That's in the second circuit.
Yeah.
So that's where you can claim if the second circuit is trainable, then you might have potential quantum advantage.
Yes. So actually, for the localization, we did not just claim we have some advantage in localization, because the localization is actually the technique that used in the Relu effect, the proof of Relu effect. They also use the same like local Taylor extension to show, I mean, this quantitative approximation error. So here we just totally ignore all the generalization and the trainability stuff. We just solely focus on the approximation. Just how large of that model that you need to approximate achieve the same level of approximation error. Then you conclude this kind of advantage over the classical model.
Yeah, you're talking about quantum models is like much smaller than got it.
Yes. So, and also we also have some constraints, so that S is upper bounded by or lower bounded by this, so it should be larger than this quantity. But it is actually easy to satisfy if we based on our previous assumption, because when the smooth index S is small and input dimension is large, which means this quantity is close to 1. Right. Yeah, so basically that's the analysis of the advantage over FNN. And here's a summary of our work. So we first show explicit construction of PQC compared to the previous unconstructive or non-constructive proof of the universal approximation theorem, which is sort of an improvement. And also we show, using that proposed PQC, we show quantitative approximation error bound using Bernstein polynomial for Lipschitz functions, and also for local Taylor expansion for Holder smooth functions. And using that, we compare the size and number of parameters of the quantum model and the classical model to a conclusion on the possible quantum advantage over the near optimal Relu FNN. Because I mean, in that table that you saw before, that approximation error bound is, for the classical one, is near optimal. So I think in this sort of quantum advantage, the key is that, I mean, the takeaway is that using the PQC, we can efficiently implement polynomials using that PQC. Because if we look back to how the classical FNN, they prove the approximation narrow bound. They also use the local Taylor expansion, which means they need to use the ReLU FNN to implement polynomials. But actually, it's not that efficient as we can do in quantum. So I think that's a key of why we can achieve this quantum advantage. And also, as I said, in the classical one, they show that the approximation narrow bound is near optimal. But in quantum one, currently we don't know that. It's just an upper bound, but we don't know the lower bound. So one interesting topic is to show whether we can do better, or it is optimal, or it is near optimal. And also, as I show in the possible quantum advantage that we can show in the quantum machine learning, we can also try to study the possible quantum advantage of optimization and also for generalization, other than the approximation that we studied here. So yeah, that's a reference, and thank you for coming.
Yeah, so thanks, Zhan, for the very interesting talk. So for the audience on Zoom, if you have any question, feel free to unmute yourself to ask the questions. And yeah, for the audience here, like, you can just ask questions. Maybe just like start with me. Over here, consider the ReLU
the ReLU FN.
Yeah, FNN. Like, how about other activation functions? Have
Yeah.
people considered that, and how does that compare to PQC?
Yeah, that's an interesting question. I think for this paper, the author recently they had a new paper showing that using other activation function compared to ReLU, they are like in the same order, which means that our results could maybe generalize to other types of FNN using different types of activation functions.
Right. And
So
yeah, and then it's like, how about different kind of like neural network structure too?
yeah, that's a good question. I think so. When we try to say quantum advantage, we want to specify the target that we want to compare. Here we just compare to
Right,
this
it's just like
specific.
starting point for people to start comparing.
Yes.
Okay.
So that's why that maybe you asked the quantum advantage. I think it is not sort of the typical quantum advantage that we talked before, because like in short algorithm or a Grover's algorithm, that sort of quantum advantage is that we have a quantum algorithm which is like exponentially or like polynomially more efficient than any known classical algorithm. But here we just choose a specific target, the target model that we want to compare. But we cannot say that PQC is have some advantage, or say exponential advantage over all classical models. We cannot say that, right? Yeah. But that is I think interesting question.
Yeah, the other question that I have is that because you know the form of function that you want to approximate, right? Then that means you can also construct a classical surrogate for that, right? Like, for example, for typical like rotation encodings, right? And the output observables will be written in like Fourier series. And people have directly used the Fourier series of like and then trying to approximate your PQCs, right? Yeah, and then so over here, I think it's possible to do the same for your case, and how would that be? Because like in their papers, they are saying that okay, even though you can kind of learn PQC, but then during the training process, maybe you can use PQC to train. Like, would that be the case for your construction over here as well?
Yeah, it could be possible, because here, maybe as you can see here, we use nothing but just the local Taylor expansion, which is basically polynomial.
Yeah.
Could be efficiently implementable by maybe classical computing.
Right.
Yeah,
Uh-huh.
it is true.
Uh-huh.
But yeah, I don't know for this question. I think it is
Yeah, it's a tough
interesting
question.
topic.
It's a
Yeah.
tough question to answer, to be honest.
Yeah. So yeah, basically I find that maybe it is a good question to ask why people in classical machine learning they choose to use this sort of neural network
Neural network instead of like
instead of the Fourier
Yeah.
series or the Taylor series.
Yeah.
Why they want to avoid
Yeah.
that?
I think that definitely there are a lot of people working on that, and we just have to go and
Yeah,
check it out and try to bring it up.
Yeah. So yeah, I guess that so one thing I would know is that if we classically use the polynomial or say the Fourier series or Taylor series to do the approximation, you'll have curse of dimensionality. That's probably one of the key problems that people tend to avoid using them in machine learning. But here you can see even in the quantum setting, we also have some curse of dimensionality because here in the arrows or the number of parameters or depths, we'll always find that I mean there's because k is what you can choose in deciding the size of the model. Because you cannot choose the target function. Target function is given. Yeah. You can just change k. Yeah. But once you change k, you'll find that the size or the number of parameters of both of the classical model and the quantum model, they will increase exponentially as d increase. So I think the curse of dimensionality cannot be avoided, even in this case. Right,
unless you kind of like know exactly, like nowadays people like to kind of like use the term inductive bias, basically trying to find a structure in the problem and encode in your and then define your parameters or your model accordingly, for example.
Yeah. So basically, based on what we discussed, we can actually say that I mean this kind of advantage in the for people in classical machine learning, they will consider the d and s to be a constant vector because that's not what you can control. And what you can control is so they will say that the classical one and the quantum one are in the same order.
Right.
But actually here we just compare the so-called constant vector. So we can achieve this sort of exponential improvement over the classical one on the constant vector, or say the factor related to the target function.
Right.
But not in the k. For the k, I think that almost the same.
Right.
Yeah. Once you like for the same d, when you increase k, once you increase k to have a better approximation results, you will have curse of dimensionality.
Right.
Can I ask about your? I think you had some numerical results. But can I ask how many parameters you have?
Oh no, we don't have. Yeah, we don't have.
Yeah.
That's a purely theoretical.
No, then we get a diagram that shows the Fourier function. And
oh yeah, that's just using the I mean the polynomial.
Okay,
itself.
so there wasn't
It's not. It's not.
If I understand correctly, the other uploading circuits you would propose is something which is quite friendly for this. You can for near-term devices because you can deal with parameterized gates.
Yeah.
But then your asymptotic analysis here seems to suggest it's for fault tolerance computer. So
yeah, I guess for this question, I can show you maybe the detailed construction of our result. So typically we will consider the linear combination of unitaries as a fault tolerant algorithm, right? So, but if we look at the construction of our PQC, localization has nothing to do with fault tolerant, right? It just PQC is not entanglement. It's just a tensor product of single cubic PQCs. But for time expansion, we do have, we do need to use the LCU to do the, to aggregate the single element together. But in fact, since all the gates that we want to control is actually a single cubic gate. So when we apply LCU on this entire block, we just need to apply single cubic control gate. Right? So it's not control this kind of multiple cubic block. It just control these single cubic gates one by one. So so based on your question, I think actually when we calculate the depth or the width of the quantum circuit that we propose here, we just sort of decompose them into single cubic gates and CNOT gates to calculate them. Which means we can.
So the single cubic gates are the continuous gates.
Yeah, it's just like single cubic rotation gates.
Okay, so then what? So but then if I thought correctly, your approximation error analysis does not include an error for the single cubic gate.
Yeah, that's not.
Okay.
It's not. We just have ideal gates. But I guess it's not sort of near-scale algorithm because we may need a super deep PQC. Even we have some advantage over the class one, we still need some, as you see in the with steps and the number of parameters. You can see it's still not that. We cannot say it's a shallow circuit, right? So yeah, I don't know. I think it's sort of like between the NISC and the fault tolerant, because it does not require many advanced techniques like oracles or something, but it do require some like deep quantum circuit. But basically, we can use, as I said, simply CNOT gate and single cubic gates to implement all the PQCs that we need here.
Do you have any like future work on this? Do you have any like future work on this, like investigating the trainability and things like that?
Yeah, I'm actually thinking about this.
No, I think I like your work. It's really nice. Like it's like one of the few papers that show, like you mentioned, like how like anything that's not univariate, there's no like they show that exists a model, but there's like not any kind of like how to design it or how to construct one, and you give one. So it's like a one big thing that I really like it. But the thing I don't like is that it's deep and the
Yeah.
once it's deep, and you mentioned it is deep and expressive.
Yes.
And with depth and expressiveness comes parameterized. So I like the model very much, but then the first question.
Yeah, for this one, for the optimization, say the trainability of this quantum circuit, I'm trying to say that.
Forget about quantum advantage. Just
Yeah, parameterized, right?
that's the only thing that's like solving every possible risk.
Yes, yeah, actually, it's the next project I'm currently working on to show that whether this sort of, we just simply apply LCU and actually the single QMN or say PQC together, whether this sort of results or say this sort of structure of PQC have parameters to problem. We don't know.
And what about like over parameterizing? What happens when you over parameterize this model?
Yeah, then it will be, yeah, you will get a really, really deep PQC and.
But would that have better convergence or?
Yeah, the problem is that we currently cannot do numerical experiments. So I'm trying to write some code to show, yeah, because what I know is that for the single qubit one, even if it's like super deep, and it has very good expressivity for the univariate function, it does not have anything about any problem of trainability.
No, that's because the Hilbert space is like small, right?
Yes.
Once you go multi-qubits, your Hilbert space expands exponentially.
Yes.
And that's where your variability becomes variation.
Yeah.
No, yeah.
But
I think everyone has the same.
yeah. So basically, for parameter, I think it also requires say the number of qubits to be like relatively large. So, but I guess in this sort of case, for our case, you can see the number of qubits not that much. And also we simply just use some ancillaries. And the key part of our the ancillaries is used to do the LCU, right? Just to introduce to add the single qubit unitaries together. But for the, I mean, the real part of the parameterized part in that PQC is not that much, I think. So yeah, that's an interesting question. I'm also trying to figure it out.
Okay, cool. I think maybe you can close seminar now, and thanks again,
Yeah,
speaker, for
yeah.
the very interesting talk. And yeah, so see you guys next time then. Bye.